On May 14th, 2025, the Sun gave us a powerful reminder of its immense energy. On that day, an X2.7 class solar flare, the most intense of the year so far, erupted from the active region known as AR 487. This event not only caught the attention of the scientific community, but also caused large-scale radio blackouts across regions like Europe, Asia, and the Middle East. It served as a direct reminder of how solar activity can almost instantly impact our deeply tech-dependent world. In this video, we're going to break down what this flare was, its immediate effects, and what it means for the future of our global infrastructure. Solar flares are classified based on their X-ray brightness, measured in wavelengths between 1 and 8 angstroms. The categories follow a rising scale, A, B, C, M, and finally X, with X being the most powerful. With each step up, the intensity increases by a factor of 10. An X2.7 flare, therefore, is 2.7 times stronger than an X1.0 flare, which shows just how massive the May 14th event was. The flare peaked at 8:25 Universal Time Coordinated, releasing a massive amount of energy that hit Earth's upper atmosphere almost instantly, as radiation travels at the speed of light. The solar region AR 487 had already been showing signs of instability the day before. It produced an X1.2 class flare. On the morning of the 14th, before the main event, it had already unleashed an M5.3 class flare. These were clear signs that something bigger was on the way. Indeed, the Sun was building up to a major energy show. As soon as the X2.7 class flare erupted, extreme radiation, including X-rays and extreme ultraviolet radiation, directly hit Earth's D layer of the ionosphere, causing a sudden and intense ionization. This process led to serious disruptions in high-frequency HF radio communications across the sunlit parts of the planet. In other words, radio transmissions between 3 and 30 megahertz simply stopped working or became extremely unstable across large parts of Europe, Asia, and the Middle East. Industries that rely on these communications to operate, such as aviation, maritime navigation, and emergency services, felt the impact immediately and alarmingly. Although the flare itself didn't produce a coronal mass ejection, CME, directly aimed at Earth, the threat is still in the air. Region AR 487 remains active, and as it rotates into a position more directly facing our planet, the chances of a future CME hitting Earth's magnetic field increase, potentially triggering a powerful geomagnetic storm. The immediate effects of this powerful solar flare were felt in many parts of the world. The disruption of high-frequency radio communications hit strategic sectors like aviation and maritime navigation, especially affecting flights that rely on this type of signal to coordinate routes and stay in contact with control centers. Under normal conditions, these signals travel long distances by bouncing off the ionosphere. But when this layer becomes abruptly ionized, as it did during this event, those waves get absorbed or deflected, making communication unstable or even impossible. Beyond the communication failures, the consequences of a solar flare of this magnitude go far beyond what we notice right away. Intense ionization also affects satellite navigation systems like GPS. While it's easy to think of GPS as just a tool for driving directions, it's actually critical for power grids, banking systems, precision agriculture, and even commercial aviation. When these signals are distorted or delayed by turbulence in the upper atmosphere, the impact is felt across many areas of the economy and daily life. Another critical issue involves satellites in low Earth orbit. During events like this, solar radiation heats up the upper atmosphere, causing it to expand. This expansion creates increased atmospheric drag, almost like the satellites are pushing through thicker air. That drag can alter their orbits, requiring constant adjustments to keep them on their planned paths. Fortunately, the May 14th flare wasn't accompanied by a strong CME capable of triggering such extreme effects, but experts are still on high alert, and it's not an overreaction. When a CME directly hits Earth's magnetic field, It can unleash powerful geomagnetic storms capable of knocking out entire power grids, damaging transformers, and even accelerating corrosion in underground pipelines. Not to mention the increased radiation risk for high-altitude flights, especially those over polar regions, and for astronauts on missions beyond the protection of Earth's magnetosphere. Considering all this, it's increasingly clear how important it is to strengthen our systems against space weather threats. Monitoring the sun's behavior is no longer just an interest for astronomers. Today, it's a matter of global technological and economic security. Modern infrastructure is deeply interconnected, literally by radio waves, satellite signals, and power grids. A failure in any of these systems can trigger devastating ripple effects. And as these solar events become more frequent, the urgency to prepare grows stronger. The recent episodes of solar activity are a clear warning of what's ahead. We're approaching the peak of solar cycle 25, expected later this year, and all signs point to an increasingly active Sunday. Like every other cycle, this one lasts around 11 years and alternates between periods of low and high activity. And if recent events are any indication, we can expect even more solar storms in the coming months. In 2024, for example, region AR 3664 shocked the world with an X8.7 class solar flare, one of the most powerful in recent decades. That happened on the exact same date the year before, May 14th. Coincidence or not, the impact was so strong that it triggered a rare G5 class geomagnetic storm, the highest level on the scale used to measure these events. The effects were felt across the planet. Spectacular auroras lit up the skies in unusual places like Texas and Spain, while navigation and communication systems experienced failures. In some cases, flight routes had to be changed to avoid areas with increased solar radiation exposure. But that wasn't an isolated incident. Throughout 2024, other intense flares were recorded, including an X6.3 on February 22nd and a massive X9.0 on October 3rd. A true solar monster, as some experts described it. Even though not all of these flares were accompanied by Earth-directed CMEs, they clearly showed the sun's increasing instability. It's as if our star is sending louder and louder signals that its stored energy is reaching critical levels. What we're seeing in 2025 confirms this. The same region that produced the X2.7 flare, AR 487, had already generated an X1.2 class flare the day before and an M5.3 on the same day. These back-to-back events show that we're not dealing with isolated flares, but rather with a highly unstable region of the solar surface. As it continues rotating toward Earth, the risk of new flares and CMEs aimed directly at our planet increases significantly. To deal with this scenario, continuous monitoring of solar activity has become a top priority for agencies like NASA, ESA, and NOAA's Space Weather Prediction Center. Satellites and observatories like the Solar Dynamics Observatory, SDO, and the Parker Solar Probe are on the front lines of this mission. They not only observe the sun's outer layers in real time, but also gather data that helps improve the accuracy of solar storm predictions. This gives us a time window, sometimes hours or days, to make critical decisions and prevent major damage. It's exactly that window between a solar flare and the arrival of a CME that can make all the difference. While flare radiation travels at the speed of light and reaches Earth in minutes, CMEs are slower, taking anywhere from a few hours to a few days to arrive. That delay offers a valuable opportunity for satellite operators, airlines, power grid managers, and emergency services to take preventive action. But the real challenge is prediction. Not every flare comes with a CME, and not every CME hits Earth. We're still learning how to identify reliable patterns in this increasingly unstable context. Investing in resilience is no longer optional. It's an urgent necessity. Governments and companies are already working on ways to shield satellites with stronger protection, reinforce electrical substations, and build redundancy into GPS systems. But technology alone isn't enough. Education and awareness are essential too. Just as we've learned to deal with hurricanes and earthquakes, We must understand how the sun behaves and the risks it brings so we can be better prepared. The X-2.7 class solar flare from May 14th, 2025 is not just another number on a chart. It's a clear sign that we're entering an intense phase of the solar cycle where events like this may become more frequent and more dangerous. The sun, the star that warms and sustains life on Earth, can also shake our modern structures in the blink of an eye. That's why, as we move through the rest of 2025 and approach the peak of Solar Cycle 25, global commitment to vigilance and preparedness will be crucial, not just to protect our technology, but to safeguard our future. If you enjoy following the mysteries and dangers of the universe, don't forget to subscribe to the channel, leave a like, and activate the notification bell. That way, you won't miss any videos about the fascinating and sometimes threatening world beyond our atmosphere. Thanks for watching, and see you in the next one.